today, right now, we're doing grade 11's physical science, and we're chatting about chemical bonding and an introduction to electronics. And Phil, our wonderful teacher for grade 11 for today, will be taking us through this. Okay guys, let's get going.
Absolutely, and thank you for that. Well, today's lesson we're going to be talking a little bit about semiconductors, and one of the things that I really want to talk to you about is why semiconductors are that important to us. The screen behind me, the television that you're watching this on, even the computer that is being worked on next to me, based on semiconductors. Now, they haven't been around that long in terms of electronics use. Around about 50 years of transistor and diode use, and we're going to talk about how these wonderful things work. Microchips, microcontrollers, LEDs. I'm sure most of you have got a phone in your hand and you're busy watching the TV. You've got a calculator in front of you. All of these depend on silicon chips. Now, what I'm going to be doing is I'm going to be taking a look at a very small area on the periodic table today. We're going to be paying attention to parts which lie on the boundary between metals and non-metals. This boundary is very often called the metalloids or the semi-metals. Now, the really cool thing about these semi-metals is they're kind of like metals and they're kind of like non-metals. This means that I can tell them when to be a metal and when to not be a metal. Now, the great thing about metals is that they can conduct electricity. They have all these free, loose electrons. If you remember from last year in grade 10, we talked about metallic bonding. We had loose valence electrons. Now, what's happening when we move from aluminium and gallium and germanium into these semi-metals like silicon is that silicon, we can tell the electrons when to move and when not to move. Other cool thing that we can do is we can mix up silicon with other types of elements, and this means that we can control the way that it behaves. So if we've got silicon right in the middle here underneath carbon, hugely important elements. Carbon itself can be semiconductive as well. I can take carbon rods. The lead inside your pencil is not actually lead. It is graphite, which is a form of carbon. Silicon itself is the stuff which goes inside chips. This is the magical stuff which Bell Labs in 1947 managed to make into a transistor, and this paved the way to make computers, cell phones, even the satellites which are relaying some of this material to your television screen right now. You're using silicon at the moment, which is amazing. So what I'm going to do is I'm going to pick and choose a few of these metals along this boundary between metals and non-metals, and we're going to put them to some use. We're going to try to see if we can't make our very own semiconductors. So just taking a look at some of these semiconductors that I'd like to pay attention to. Silicon is a great one. This is the one that we use nowadays. What we're going to be doing is we're going to see what happens when I combine silicon with other elements along this line. I'm going to pick elements from the groups next to it. The one which I've chosen for today's lesson is boron and arsenic. Now, the thing that I know about arsenic and boron is they're both very toxic, but that's not why we're talking about them today. The one thing that boron and arsenic can do is give silicon very special properties. When we add these two compounds to silicon, we call this doping. Now, just as in sport, doping is the addition of something foreign to change the properties or the performance of the silicon that we're going to be talking about. Okay, let's move a little bit further and let's see how we can combine silicon with boron and arsenic. So, if we take these elements and we start taking a look at how they are structured. I've got boron over here, I've got silicon over there, and I've got my arsenic on the right-hand side. What we're going to do is we're going to talk about why these electrons are very important around them. I see that boron has got 3 valence electrons, silicon has got 4 electrons, and arsenic, I've actually chosen to show you that extra electron in gray. And the reason for that, I'm going to show you in a moment. Now, where do these numbers of electrons come from? Now, it's very easy. If you look at your periodic table, you'll see that group 3 in Roman numerals has got 3 valence electrons. If I've got group 4, 4 valence electrons, group 5 has got 5. It couldn't be simpler. What we're going to do with them is we're going to play around with them, make some chemical structures. So, let's start playing around with these ideas. I'm going to take boron, I'm going to take silicon, and we're going to build our very own semiconductor. Now, if I start making a little bit of space, and I want you guys to do the same with me, you're going to draw these structures in with me. I'm going to take silicon, and we're going to start playing around with it. I'm going to start linking it up to itself. I'm going to start linking it up with other elements. So if I link up an element like boron, I need to take my electrons and see how many electrons need to go with it. One of them is going to find itself in the bond over there. I'm going to find the other electron in that position and the other one right down at the bottom there. I'm dragging another boron there. Okay, we don't need 2 borons for the moment. Let's leave that off to the side. Now, you'll find if I try drag this all over and I try add in another silicon, we're going to be presented with a little bit of a problem. If we move this across and try add in another silicon over here, you're going to find a lonely electron. There's a space where there should be another electron. Every other place where you see silicon bonding onto boron, boron onto silicon, I've got these 2 electrons. So I'd just like to highlight that. So in every space where I make a bond, I've got 2 electrons. However, what I see over there is there is a missing electron. So what that does is it leaves a space for another electron to join in. That's quite an important thing to do. So let's just get rid of that for the moment, and let's start playing around with some of these other elements. Let's just make space. It's a little bit cluttered over there. Okay, but now let's see what happens when we join on silicon and arsenic. So if we join silicon onto arsenic, when we pair up those 2 electrons to make that bond, that covalent bond in between them, we can see that there is the 2 electrons. If I put another silicon on the other side, we don't see this empty hole anymore. I've got an extra electron up at the top. So one thing that I'd really like to drive home is that arsenic has got an extra electron, boron has got the 1 missing electron. Now, how does that impact things going into this? I know that my boron had that 1 gap. I'm going to put that off to the side and we're going to draw all over it. This creates something which is called a hole. It's a positive hole because there is a missing electron. Remember that whenever you've got electrons and electrons are negative, any place that they are missing from becomes positive. Sometimes these are called positive holes inside this material. I call this type of material, which is silicon mixed with boron, a p-type semiconductor. This has been doped with boron. Let's see what happens when I dope it with something else. Remember that boron was from group 3, had my 1, 2, 3 electrons, and left the space. So what we're going to do now is we're going to see what happens when arsenic enters the picture. Arsenic had that 1, 2, 3, 4, and I want you to notice that there's an extra electron floating around. Electrons are great for conducting electricity. That means that I've got this electron which can go somewhere. Some of you might be thinking, how can I use p-type with boron, or how can I use n-type with arsenic all on its own? Well, silicon doped with arsenic is quite conductive all on its own, but that's not where the magic lies. The magic lies when I combine these 2 types of doped semiconductors. I'm going to take my p-type and my n-type and combine their powers together to do something really magical. I can control the way that electrons flow. Let's take a further look on how we do that. Now I'm going to take my silicon, which is doped with boron on the one side, put it on one side, and I'm just going to call that my positive region. Why do you suppose I call that my positive region? Well, it's really not too difficult if I remember that there's a gap sitting on the one side. The hole where the electron used to be, which I've circled in red, is where there's a space for an electron. So when I put that back there, I can see that there's a space for an electron to go. Some of you have already tied this picture together. What I'm going to do is I'm going to highlight where that electron is going to come from. I can see that there's an extra electron on the one side and there's a gap for it on the other side. So what that does is it creates a natural way for electrons to go. There's too many on the one side and there's too few on the other side. What that allows is electrons to flow from one side to the other side, but not from the other side back. So let me just get this all straight. A lot of people are confused and there's all these new terms going on. I've got a p-type on the one side, I've got an n-type on the other side. How do I see which way electrons are controlled? Well, remember that arsenic has got the 1 extra electron, so this is called my n-type. The other side, which has got the missing electron, is called my p-type. If you're worried about remembering that, I've written it down here for you. My p-type, remember, was from the group 3 element. Let's just write that in because my group 3 element, boron itself, is a group 3 element. whereas silicon was group 4. So you can see that a group 3 element has one less electron than the group 4 around it. What about arsenic? Arsenic had that one extra electron because arsenic itself was from group 5. Now if I remember that group 3 and group 5 are 2 electrons apart, we can see where the electrons are coming from. I've got my extra electrons in my n-type, my negative type. I've got my missing electron in my p-type, or my positive type. Now what that allows is for electrons to flow in one direction. Now this is the magical thing. This device is called a p-n junction for obvious reasons, because I've got a p-type and an n-type stuck together. They are joined together in a junction. I've got a p-type on the one side and n-type on the other side, and this particular device revolutionized electronics. What this did was it told the electrons where to go. And if I can tell the electrons where to go, that means that I can build electronics, I can build computers.
Can I ask a question?
Absolutely.
I don't know, a few viewers have said that they're finding it a bit difficult to see the diagram. I don't know. Maybe what we can do is maybe draw a simpler one. I mean, maybe the mind setters would like that if we have time to do that.
Not a problem at all. We can make space for that.
Okay, fantastic.
Okay. So what I'm going to ask that you do is you follow an exercise with me. I'm going to draw a p-type and an n-type separately. Cool. Would that help them?
Yeah, I think that would help a lot.
Fantastic.
Awesome.
Okay, a lot of people really get very anxious when they see Lewis dot diagrams. They're not sure where all the electrons go, how to make all the bonds. So let's actually follow through from this from step 1.
Perfect.
Okay, so what I'm going to do is I'm going to draw in 2 different colors so that you can see where the 2 different elements are, where they're coming from, and how they come together. So our first guy, silicon, I'm going to draw in red. And remember that silicon was a group 4 element. So if I've got silicon, remember that 4 electrons would be spaced evenly around it. Now what I'm going to do is I'm going to show you or remind you how to make bonds with Lewis dot diagrams. So a group 4 element like silicon shows me that I've got my 4 electrons. Now one thing that I'm going to be doing is I'm going to be drawing the other 2 types of elements again. Now, on the one hand, I had my group 3 element. If you can remember, that was boron. Boron has only got 3 electrons. Okay, now this is where you need to pay real attention. What I'm going to be doing is I'm going to be drawing them together, but I'm going to be switching colors to keep them separate. Now, it's going to get confusing if I draw everything in red, and I think that's where the viewers might have got confused. Okay, so we're going to take our silicon, we're going to bond it to boron, and we're going to see how they interact with each other and where the missing electron comes from. So silicon is amazing stuff. I'm going to put boron in the middle. So let's switch to a different color. Let's make boron the one right in the middle. Let's draw its 3 electrons, then we'll worry about the silicon around it. Now a lot of grade 11s really struggle to draw this diagram and where to draw all of these things. Now, the thing which really helps me, I'm not going to leave them in place, is that every atom has got these imaginary post boxes which are drawn around it. Most atoms have got 4 post boxes which you can draw around it and spaces for them. I start in the first position and then I draw the next one and then the next one and then the next one. Once I've got 1 in each slot in the post box, then I start to make pairs. But we'll get there later. Let's take this very slowly. So let's get rid of our post boxes. They're meant to be imaginary. Let's just take them away because we need that space to draw with. Okay, so far we've only got boron. Let's put some silicon in there. Now silicon, as you can see, has got all these unpaired electrons. I've got silicon over there. Let's not leave that guy behind. I'm going to slot silicon into its place to make electron pairs. Now these electron pairs, where do they come from? Well, any electron likes to have a partner. So I like to make pairs between those 2. I've got a possibility that I can pair any one of these 2. Let's see how it happens after we've paired a couple of these silicon items with the boron. So let's switch back to another color and let's draw a silicon atom next to my boron. We're going to make a bond together. So I've got silicon with its 4 electrons, but one of them has now taken up a new home with my boron. I've made a bond, a covalent bond. The reason that I know it's a covalent bond is because I've got a metal and a non-metal. They are sharing electrons. I'm pretty sure that you can see what I'm going to be doing with these next 2 electrons. So if I've got silicon, I can make the pair up there, then my other 4 electrons are surrounding all the way around there. I can do it again on top as well. Another silicon, another pair. So I've got now silicon evenly paired over there. But now if I draw another silicon, you're going to see something very strange happen. Once again, I've got my silicon, I've got an electron, I've got an electron, and all 4 are surrounding my silicon. But there's something missing. Remember those letterboxes around here? Boron had 1 letterbox, 2 letterbox, 3 letterbox, and the 4th letterbox is actually standing quite empty. Let me just draw in those letterboxes I was talking about. If I draw in letterbox number 1, letterbox number 2, letterbox number 3, and 4, you'll notice that there's a gap. There is no actual chemical bond between the silicon and the boron. But the engineers that make this stuff are very, very clever. What they do is they ensure that the silicon crystallizes with the boron. And what that allows me to do is have a silicon crystal with missing electrons. Very, very clever. Can you remember if this is p-type or n-type? Well, if I've got a missing electron, and electrons are negative, and they've gone away, that means that I leave behind positive. I know that's a lot to take in, but what I'm going to do is I'm going to practice with you again. Let's try this with the n-type semiconductor again. Okay, so back to silicon, but now what we're going to do is we're going to practice with the n-type doping agents. So our doping agents for our silicon over here, so silicon once more had my 1, 2, 3, 4 electrons in the letterboxes. I'm going to be using arsenic in this case. One of the really strange things that arsenic is famous for, apparently it killed Napoleon. Now arsenic, if I start posting in my 4 letterboxes, I run out of space quite quickly. What I need to be able to do is place 1 as a pair. Now, one thing that you'll notice is that silicon hasn't actually got a place to add onto my arsenic. If I put my arsenic and my silicon together, what we're going to find is that there's not actually space for all the electrons. So let's try that together. I've got my silicon once more next to my arsenic. My arsenic is on this side. If I start drawing my arsenic electrons around here and my silicon bonds to it, we're going to see a problem quite quickly. I've got my arsenic with my 1, 2, 3, 4, 5. What else? I've got my silicon, which is going to make its bonds with its 1, 2, 3, and 4 over there. Silicon has now bonded to arsenic.
Why are we bonding silicon to arsenic again? I was just wondering.
Oh no, absolutely. Why am I bonding silicon to something foreign? Why is that something inside there? And what's happening is that this arsenic is taking some of its own properties and adding it to silicon. When we add the two together, their properties are going to combine. Now arsenic, because it's bringing an extra electron, is going to change the way that silicon behaves. So let's try and see from the electrons why silicon behaves the way that it does. If I've got silicon and I bond it again to the bottom, and I've got that electron from silicon adding in there, so I've got my 1, 2, 3, and 4, and silicon is behaving very nicely because we're going to put it in again. So I've got my silicon with its 1, 2, 3, 4 electrons. We're going to have a problem here. When I add in my last silicon inside the crystal, we're going to bump into some space problems. Can you see that if I insert an extra electron there, there's a little bit of crowding going on inside that post box. So what happens is, inside this post box, I have an extra electron from arsenic. Arsenic is allowing us to have an extra electron which is not meant to be there. There are too many electrons. Now, hopefully you can remember that electrons are negative, and if electrons are negative and there's too many of them, this stuff is going to be an N-type semiconductor. I hope that you can see that. So I've got my N-type semiconductor. It is negative, that is my N-type doping agent. I hope that answers the listeners' questions.
Yeah, it does. Thank you.
Absolutely. Now, how do I use this? We started talking about N-type and P-type coming together to make this amazing device. Well, let's get back through there. One of the reasons that we do all of that is to create this thing. Now, this is a circuit symbol.
And is this a practical example of what it would be used for?
Absolutely.
Labriel wants to know, can you please explain how a PN junction basically works and how a junction diode works?
Absolutely.
Is this what we're going to go through now?
Absolutely. This is what we're talking about.
Okay, well, there you go.
Okay, now this is a circuit symbol of a diode. This is a PN junction diode. All that a diode does is it controls where the electrons go, if they flow in one direction and don't flow in the other. Now, I think of this very much as a valve. And the things which came before diodes were actually called valves. Now, some musicians prefer not to use diodes and they actually prefer to use valves as well, especially guitar players. And guitar players like to use valve amps because they give a slightly less controlled feeling. But now diodes are for the ultra precise and for the digitally enhanced products. So if I've got my diode over here, this is representing my PN type junction diode. The question is, how do I use one of these inside a circuit? I'm going to take this symbol and make the magic happen. So if I connect up a diode, there is one way that I can connect it so that electrons do flow. Then we're going to see why they don't flow if I try the other way around. Okay, so I've got my diode, I've got the symbol in front of me, and I'm not exactly sure what's happening. I've put a plus on one side and a negative on the other side. Now, the way that I've connected it will allow electricity to flow. So this means that the valve is open, there is current flowing, and electrons are moving in the direction that I've shown you on the screen. Remember that electrons flow from negative to positive. Now, a lot of you are shouting inside your head, but that's not the way that current flows. And that is absolutely correct. There are two types of current. Before electrons were discovered, they actually thought that current went from plus to minus, and it's still used in textbooks and science that way. This is called conventional current. I'm going to draw it in with an arrow. A lot of you will have drawn this in grade 10 and 9 before. So conventional current goes from plus to minus, although electrons flow in the opposite direction. One of the really cool things that drawing in conventional current shows me is if my diode is going to conduct. This arrow that I've drawn in is in the same direction as my diode. So if I shift it over, I can see that those two are in the same direction. If conventional current is in the same direction as this arrow inside my diode, this means that my diode will conduct. I call this a forward biased diode. Forward bias means that I allow current to flow. It lets the electricity happen. Now, a lot of people are saying, okay, well, what's the big deal? All I do is put in a wire, it will conduct electricity. Now, the real magic comes in is if I swap these two around. If I take my negative and I take my positive and switch them around on my diode, what you will find is that absolutely no current will flow. So if conventional current tries to flow inside here, what we're going to do is try and reverse my conventional current. What you'll see is that it can't flow. I can't have conventional current flowing into there because these arrows don't match. They're in opposite directions. One of the reasons that the symbol has got a line over here for the N-type and the P-type is that I've actually got a blockage from plus to minus. So if I tried, I couldn't get currents to flow in a positive to negative direction. So the purpose of this diode was to stop all of that from happening. So I allow current to flow in one direction, but not in the other direction. Now that's especially important when you take a look at electronic devices. If you look inside your cell phone, and even if you open it up and look inside at the battery, you've got a plus and a minus. If you plug that in the wrong way, you actually destroy the battery altogether. Electronic devices really need plus and minus to be the right way around. A PN junction is the way that we get electrons to flow. What else are our callers saying?
There are quite a few. Rishan Naidu wants to know, what is a forward biased diode? And okay. Is that going?
Okay, well,
okay.
in case he wasn't listening earlier.
Yes, that's right. What I thought. I thought maybe you cleared it up, maybe you didn't.
It's absolutely entirely possible that we didn't cover it properly or that somebody didn't understand it. So remember what happens when a diode does conduct. That is what we call a forward biased diode. I'm going to make this diode forward biased. Let's keep the negative on that side. Let's drag the positive. If I connect, it's busy sliding off the page away from me. Right, but if I connect plus to this side, plus to the p-type, this is the way that I remember. Plus for p-type, N for negative type. This is the easiest way to remember if a p-n junction is forward biased. That means that it allows current to flow. Let me just draw in our current again. My conventional current will flow if there is a forward bias and if I've got plus connected to P, negative connected to N-type. It's the easiest way because a lot of people are saying, well, I don't know which one is connected to which, but it's quite obvious if I remember that N is for negative and N-type is the one to match it up with. That is a forward bias diode.
So guys, if we don't get your questions on the page, I'm really sorry. What we'll try and do is we'll try and get teachers to come back and write in those answers. You just have to give us about 48 hours to get back to you, because don't forget that our Facebook page is a help desk. If there's anything you don't understand, please show us where you don't understand, because it makes it easier for us. Paste the question, we will get back to you within 48 hours.